we have our energy diagram here, which shows whether it's endothermic or exothermic reaction. We see that it's exothermic reaction because the products are of lower energy. The left-hand side, these would be our reactants, and then over here we have our products. The difference in those two is the energy change in the reaction. What we're interested in today, however, is the activation energy. You see activation energy right here. Activation energy is the energy from the reactants to the top of the hill, which is where you have your activated complex. And that would indicate how much energy is needed, the minimum amount of energy that is needed to be applied in order for the reaction to occur.
Another way to look at that activation energy is to look at it in a Maxwell-Boltzmann distribution. And so you can see that there are two distributions of molecules, one at a lower temperature, the blue line, one at a higher temperature, the red line. And you can see that as you get to higher temperatures, that distribution, the Maxwell-Boltzmann distribution, shifts to the right. So you can see that if you look at the average kinetic energy of the lower temperature versus the average kinetic energy of the higher temperature, it's shifted to the right. The molecules on average have a greater kinetic energy, which allows for more of them to have sufficient energy to overcome that activation energy and to break bonds. Now what we can do is we can actually calculate the fraction of molecules that do have this sufficient activation energy, and that's going to be used with an equation called the Arrhenius equation. Now the Arrhenius equation is shown here by the fraction of molecules, F, that have sufficient energy to break that activation energy, so these molecules right here, the fraction of the molecules are going to be represented by E, which is natural logarithmic E. E sub A is going to be your activation energy. Your R value is your gas law constant. Now we are going to have to make sure that gas law constant is in 8.314 joules per mole Kelvin, because we are dealing with energy, so we do need the joule version of the gas law constant. We're also going to need to know the temperature, and to be consistent with our value of R, we're going to have to make sure that's in Kelvin. So the fraction of molecules that can react, well, just to give you an idea, let's assume the temperature is about 300 Kelvin, so a typical round room temperature. Let's also assume its standard activation energy of about 100 kilojoules per mole, which is pretty standard. That's not too high, not too low. If we were to actually calculate the fraction of molecules that had sufficient energy to overcome those bonds and to actually react, we would find that the fraction of the molecules would be approximately 4 times 10 to the negative 18th. Now that is a very, very small fraction of molecules that can actually react at room conditions, all right, with a standard activation energy. And so that's part of the reason why, like when we're doing reactions in the classroom, we want to do them at higher temperatures, we want to do them at higher concentrations, we want to do things that will affect the fraction of molecules that can break these bonds. Otherwise, the reaction is going to be much too slow. Now there is one more thing we have to take into account when we're looking at the fraction of molecules that have sufficient energy to react. We've already looked at the activation energy here. We've already looked at the temperature here. There is one more consideration, and that last consideration would be an A value, or what's referred to as a frequency factor. A frequency factor is basically, as you can read here, a number that represents the likelihood that collisions could occur with the proper orientation for a reaction. So size, steric hindrance is going to come into play here. So there are some other considerations besides the activation energy and temperature. Now when you multiply, so do realize that this e to the negative a over RT is that fraction. When you multiply that fraction of molecules times that orientation constant, you actually get a new idea or a new concept here called K. Now that K to us is going to be referred to as the rate constant, which at this point in the chapter we're going to assume is rate, or is going to be consistent with rate. Now rate constant and rate are actually different concepts, but linked. So just realize it now at this point that if we say it has a higher rate constant, it also has a higher rate. And we'll talk more about that when we start doing our rate laws. Now a lot of times what's going to be helpful is to actually figure out what the activation energy is for a particular reaction. And that's going to be useful. And you're actually going to do a lab on that a little bit later in the semester, or later in this unit. And how do you find the activation energy? Well, what's going to be really useful in chemistry is to do things graphically. And this is going to be a big thing that we do graphically. You're going to need to remember for the AP exam.
You know, what you do with the data that you'll begin with, you'll have temperature, which if it's in Celsius, you'll need, of course, to convert it to Kelvin. And then you'll have your rate constant, your small k. At these different temperatures, you'll take natural log of the k and inverse those temperatures and then represent that graphically. The good part about that is when you do that, you'll see the slope of this line is basically negative, is right here. So the slope is negative EA over R, so you can use that to find your activation energy.